All right, the last free response question. Let's go ahead and graph what they want us to graph in part A. So we have this thing, and what's going to happen is eventually we're going to be doing some oscillation stuff with it. But for now, let's just use Hooke's law to figure out what's going on here. So we got weight and length. The more weight we tie on here, the more the string lengthens. So when the weight is 0, we've got a natural length of 0.6, which is kind of highlight here. And then when we have a length of about 0.97, we have a weight of about 15, so I'll put that right there. And then when our weight is 20, we're at about 1.37. So 1, 2, 3, 4. So about 1.37, maybe about there. And then when our weight is 25, we're at about 1.64, so 1.1.6, right about there. And so we just want to try to pick a best fit line to go through all these points. Let me see if I can grab a line from my tools and actually do that here. So hopefully this works out the way I want it. This line function can be a little bit weird. So yeah, kind of. Let's see. So 1.0. Oh, you know what? This should actually be here. That makes a little bit more sense. There we go. So let's just kind of see what our graph looks like. So when we actually do this graph to get the slope, I would say that, let's be clear, the weight for, so I want to use Hooke's law. And here I'll use delta x to represent the distance from equilibrium. So this actually means F is going to be negative k times the displacement, which is going to be here. If we really want to be clear, this is what this graph would look like. I would say it's the weight is going to equal k times the length, okay, minus our little equilibrium distance. So that's going to be 20 newtons minus, actually I kind of like this. So I would say this 20 Newton thing is happening at about 1.4 versus this 0 newtons just happening at 0.6 meters. So if I go ahead and actually do this math, I'm going to end up getting 20 minus 0 over 1.4 minus 6, and that's going to give me about 23 newtons per meter when I get the slope. This is what K is actually equal to. Okay. Now for part C, we want to get the mass of the object, and this is where we need to be really careful. So we know that here mgy max, I'm just going to say the height that it falls, so we have all this gravitational energy converted into spring energy when we reach that maximum displacement. So we have here our K equal to 23 from before. So our mass, we're told, is unknown. So we have m times 10 times y max. And let's be clear, this y max is 1.5. Now this x is the displacement from equilibrium, which is going to be 1.5 minus 0.6 because it's from the equilibrium point. So that's going to be 1/2 times 23 times 0.9 quantity squared. And when we do this, we're going to get a mass of about 0.7 kilograms. And then for part D, we get max speed when the net force is 0. In other words, it's when we don't have any resistant spring force on it. And that's going to happen when mg equals kx. And that's just going to be 0.7 times 10 divided by 23. So that's going to be 7 divided by 23. It's going to be about 0.3 meters. And then why is this the point where we have the maximum speed? Let's be really clear here. So what's happening there is basically acceleration is 0. And this implies that kinetic energy is at its maximum because PE is 0 when there's no stretch. And that's at equilibrium with no net force. Okay. And then for part 3, the maximum speed of the object. Well, that's going to happen. We'll use conservation of energy there. So we know the total energy is going to be mg times y max. Okay, so that's going to be, actually, let's be clear. So we want to know the maximum speed of the object. So let's be clear. When it's at its maximum speed, we're going to have some spring energy, and we're going to have some kinetic energy. And this x is going to actually be the equilibrium distance we had before. And that's going to actually be mg times y at the Vmax. Which is going to be the 0.6 unstretched plus the 0.3 of the equilibrium. So we're going to end up getting here 1/2 k times 0.3 squared, and we'll put 23 in here, plus the 1/2 times the mass, which is going to be 0.5, and then the v squared is what we're solving for, times 0.7, and I'm sorry, I had the m wrong. This is 0.7 for the m, times 10 times 0.9 here. And when we isolate for v, we're going to get approximately equal to 4 meters per second. You might get anything from 3.6 to 4.1. Okay. So that's how we get our speed. So that is our last question, a little bit of energy there. I wouldn't put something this challenging on the test, but I think it's good to kind of practice Hooke's law.